Lesson 8, intermediate value theorem, or more commonly known, IVT. So I can tell you right off the bat, IVT is an acceptable AP abbreviation. You write IVT on a free response answer, any AP grader is going to take you to be referring to intermediate value theorem. Okay? So you won't see me write intermediate value theorem throughout our lesson. I will be writing IVT. Okay? It's just what is there. So we have done a lot with continuity of a function, right? Limits and continuity of a function. And so these are, you'll notice it says continuity, which I keep talking about, right? Will prove to be an important characteristic in many theorems for our course. In order for these theorems to be properly applied, so in order to use intermediate value theorem, one of the first things we're going to be checking is the function continuous? Because if it doesn't hit that continuity, check, like if we can't check off that it's continuous, we can't use that theorem. And that is, a very key thing to work for. So, you'll notice it says, namely, the if part, called the hypothesis, must be satisfied before we can apply the then part. And so when we get down here to looking at the intermediate value, we'll say, if it's continuous, and if this is happening, then this is true. So continuity is a big part of these if-then statements. And that's what we're going to be looking at here, if-then. So this is one of several that we'll look at this year, but it's called an existence theorem. And all it's saying is that if we meet these certain restrictions, then a certain point, a certain situation exists. It doesn't necessarily tell us what the value is. It just says the situation exists. And so it is an existence theorem. So intermediate value theorem. The IVT says that a continuous function on an interval cannot skip values. So if I use my words first, if a function is continuous meaning I start drawing it, there's no holes, there's no breaks, there's no discontinuities of any sort, right? If I'm on a certain specific interval and I draw my graph, then what it's saying is that every value in that interval will be used. There will be a value that exists at every point in that interval. Now, and I'll explain that a little bit more here. So, using if-then statements. If a function, y equals f of x, is continuous on a closed interval, so an interval where the endpoints are included, and, this is a big one, f of a does not equal f of b. That's basically saying your endpoints are not the same. Because if our endpoints are the same, technically our graph never has to move up or down. It can just go straight across from one end to the other. So, and assuming your endpoints are not equal, then f of x takes on every value between f of a and f of b. So every y value between the beginning and the end has to be used because it's a continuous function that will cross through. And I'll try and draw some pictures here to help you explain. Let's see, I don't remember what this one says. Another approach, if we know a y value, say y equals k, that resides between the two endpoints, then we are guaranteed one x value in the middle, x equals c, between the endpoints that generates a y value in the middle. That's a really good one, but I'm sure it doesn't make much sense right now just reading it in words. So I think what I want to do is I want to move into kind of some graphs here, help you kind of see it, because if you can, once you understand what's going on, it's a very logical theorem. It makes sense. It's just putting all the pieces together to show it. So right here, let's look at this example. We have A and B. So A and B are going to represent my interval. Okay? So those A and B are just kind of representing my interval. So from beginning to end. And if I have a point on A. I just randomly picked a point up high. And a point on B. Okay? Again, I picked a random high point, a random low point. Doesn't really matter. But then, so a continuous function means that somehow I connect those points, yes? Do we know exactly what the graph does? No. Okay? Maybe it just goes straight across. Maybe it goes up, comes down, goes way down, comes up. But all we know is that it's going through those 2 points and it's continuous in between. So if I draw we'll do like that. Okay? So at that point, and remember there's an A here and a B here, yes? So we have a continuous function on a closed interval, A to B. Then what we know, so right here, this is A, right? So if this is A, the y value at A could also be expressed as f of A, if you will. Because if the input is A, what's the output? F of A. Down here, we have a B. Well, if B is the input, what's the output? And that's f of B. I'm going to extend those pieces a little bit. So, A and B are my beginning and end points. The graph is continuous between those points. So what we know, sorry, trying to decide how I want to do this, it is that there is some value C in between, okay, and that this point C has a spot on the graph, on that continuous function, where the y value falls in between f of A and f of B. So this being f of C, which is also known as k up in the other approach there. Now, I'll give you a moment to get your picture. I'm going to try and re-explain it one more time. Or I don't know, maybe it's making perfect sense to you, but...
So is it like equidistant from f of A to f of B, or is it going to be anywhere in...
Anywhere in between.
Okay.
No, non-equidistancing. Okay, so if we go back to using if-then statements, if my function is continuous, which was red, on the interval from A to B, do f of A and f of B equal to each other? Are my endpoints the same? No, I've got a higher endpoint and a lower endpoint, right? So those aren't equal. Then f of x, so the y values, take on every value between f of A and f of B on that interval. So this is saying that every value from the height of f of A, between f of A and f of B, every y value has an existing value. Okay, so I could pick any x value from A to B, and y does exist on this interval. Okay, somewhere there. That's what we're saying. Okay. If we know a y value, say y equals k, that resides between two endpoints, f of A and f of B. Okay, so if k is my green, that's residing between f of A and f of B, correct? Then we are guaranteed at least one x value, x equals c, between the endpoints that generates the y value, such as f of c equals k. So basically it's just saying if you have A and B, there's a value c in between them, and its y value is going to be between A and B. That's what we're saying. Okay. This one, I was just going to do, I did a decreasing function here. I was going to do an increasing function over here. If I show there's A and B, yes. And if I'm going to pick a low point on A this time, a high point on B this time. Realize f of A is going to be wherever the point on A intersects. So my f of A is down there. F of B is going to be wherever my B intersects there. And so if I connect those, and I'm just going to, there's no right or wrong way to connect this. But here, what I want to look at, and this goes back to this bottom statement here, but right here, if we call this one C, I picked that point on purpose, that point on the x-axis, so that point is C, comma 0. Or the vocabulary word, what's the vocabulary word for an x-intercept? It's an x-intercept, it's a 0, it's a solution. These are all important words that you're going to see in the homework. Okay? And they'll pop up in our example some, but I feel like they've really popped up a lot in the homework, because I have actually worked this in homework. I'm actually ahead of the game this time. Okay? But remember, a 0, I think I'm just going to, it's another word for an x-intercept, yes? It's also another way to talk about a solution of an equation. So if you get one in homework that's asking you to find a solution, they might be asking you to find the x-intercept, the 0, or in other words, where it crosses, the x-axis, where the y value is 0, all of that. And so this again, right here you have C, yes, and then over here would be f of C, or in other words, K, which I don't even know if I put it on there. If we think about writing this inequality, I know that f of A is below 0, which is below f of B. Okay? This inequality notation, we're going to see a lot today, but this is just saying that the y value for f of A is below 0, which is below the y value for f of B. So that's a way of saying 0 is between f of A and B. And so you'll notice down here in the box, an important outcome of IVT is that it can be helpful in finding zeros of a continuous function on an interval. Or you might be asked the question, is there a 0 on this interval? And this is where you might talk about it. Okay? Over here real quick, we talked about A is less than C is less than B. And on this graph, what was it? F of B was less than F of C, which was less than F of A. And again, this is just saying a continuous function on an interval cannot skip values. So every y value exists in that interval. Okay? Now, I know I only have about 5 minutes, but if I stop here, I'm afraid you'll retain nothing tomorrow. Just saying. I feel like I would retain nothing at that point. So let's see if we can look at this first example here. Does the intermediate value theorem apply on the specified intervals for the piecewise function shown below? Be sure to explain completely. So, is there a value of C on the interval -2 to 5 such that f of C equals 1? So where's negative 2 to 5? I just kind of drew in some brackets there to help us. Is there a value of x equals c on the interval negative 2 to 5 such that f of c equals 1? So basically, is there an x value where the y value is 1? Yes or no?
Yeah.
Yeah. Where's it happening at? I'd go with 3.5. Works for me. So we can say, yes, C exists. And I was going to say on negative 2 to 5. I guess it doesn't really say what is the C value, does it? It just says, is there a value? So you could say that x is approximately 3.5. It didn't ask that, though. It just said, is there a value of C on the interval such that that's true?
So it counts even though it's not a continuous line?
Did part A reference intermediate value theorem?
No.
Okay, you're ahead of the game. So part A, did it ask anything about intermediate value theorem? They just use C, which makes us think intermediate value theorem. But just, is there a value on the interval where it would equal 1? Yes, there is. Okay, that point there. Now, B, does IVT guarantee a value of C on the interval from negative 2 to 5 such that f of C equals 1? So, if we weren't looking at this picture, we just had information. Does intermediate value theorem guarantee that value exists? And why do we not guarantee the value? And yes, we see a value exists, but the IVT doesn't say what the value is. It just says whether one has to exist. Does a value have to exist? And why not? It's not continuous. It failed the number one rule here. Okay, so does IVT guarantee? That's the key. And the answer is no. The reasoning? It's not continuous. Now, I've got fancy wording written down here. Well, not fancy, but IVT, if we use complete thoughts here, let me put it that way, not fancy wording. I feel like it's fancy when we use complete thoughts, right? No, IVT does not guarantee a value of x equals C on negative 2 to 5, since f of x is not continuous. That's the key. So if I use appropriate wording, though, IVT does not guarantee a value x equals C on negative 2 to 5, and our reason being, since f of x is not continuous. Okay. Key being not continuous, right? That's the key being. So part A was just, do you physically see a value? Yeah. So we're not saying that the value isn't there, possibly. But we're not guaranteed a value because it wasn't continuous. Okay? So I guess we'll pick up there tomorrow. I should have timed this differently, but we'll look at C and D, which have the other part, a different graph, and then we'll put it all together and do some examples where we're really writing out the wording. Okay? They're planning something.